everyone. This is Surendra from Rural Public School, bringing you Physics, Chapter 9, Laws of Motion and Force. Welcome to the school. Today we will be studying about the force and the laws of motion. And in the picture you can see Sir Isaac Newton, who formulated for us the three laws of motion. He was a big scientist, and his Newton's three laws of motion are: every object persists in a state of rest or uniform motion in a straight line unless it is compelled to change the state by forces impressed on it. Law number 2, force is equal to change in momentum per change in time. For a constant mass, force equals mass times acceleration, that is F is equals to ma. Law number 3 states for every action there is equal and opposite reaction. So these three laws are very important in our life in day-to-day operations. Newton's first law: balanced forces, no change in motion. Unbalanced forces, change in speed and direction. The explanation here is an object at rest will remain at rest always. An object in motion will also remain in motion unless acted upon an unbalanced force. It's like an example: a stone remains there static for years together unless there is a force applied on it. An object in motion, like it keeps in motion unless a brake is applied on it. So you can see when a vehicle is on the move, unless there is a brake applied, it doesn't stop. So these are simple examples, and we go forward with the second law of motion. The acceleration of the object is proportional to the applied force divided by the mass of the object. Mass is defined as an amount of inertia in an object containing, that is, inertia is the resistance of an object to acceleration. Acceleration is equals to F by m, or F is equals to m into a. The third law of motion states that when an object exerts a force on the other object, the second body exerts the same force in the opposite direction of the first object. That is defined in mathematically below. Though the force is equal, the accelerations are not the same. The spaceship is more massive and will experience an acceleration to the right that is much less than what the astronaut will experience to the left. These are simple explanations about the laws of motion. We go further into this. Is another scientist, great scientist in the 16th century, Galileo. Galileo claimed to have seen mountains on the moon, the Milky Way made of tiny stars, and four small bodies orbiting Jupiter. In his book Discourse of Floating Bodies and later on the sunspots, he disclosed his observations on sunspots during his own telescopes and through his observations on Saturn and Venus. Galileo argued that all the planets must orbit the Sun and not the Earth, the contrary to what was believed at that point of time. This is a picture of Galilee Galio. Force. When you move the box with a small force, the box does not move because of the friction acting in a direction opposite to the push. In the figure explained below, shown below 9.4 and also refers to your textbook picture, this friction forces arise between two surfaces in contact. In this case, between the bottom of the box and the floor is the rough surfaces. It balances the pushing force and therefore the boxes does not move in the picture B. The children pushed the box harder, but the box still doesn't move. This is because the friction force still balances the pushing force. If the children push the box a little harder, the pushing force becomes bigger and the friction force. In the picture C, there is an unbalanced force, so the box starts moving. What happens when we ride a bicycle? When we stop pedaling, the cycle begins to slow down. This again because of the friction of forces acting opposite to the direction of the motion. And in order to keep the bicycle moving, we have to start pedaling again. If we push If they push the remote completely, the object would continue to move with a velocity it has acquired till then. It thus appears that an object maintains its motion under the continuous application of unbalanced force. However, it's quite incorrect. The object moves with a uniform velocity when the forces pushing force and the frictional force acting on the object are balanced and there is no net external force on it. If an unbalanced force is applied on an object, there will be a change either in its speed or in its direction of motion. Thus, to accelerate the motion of an object, an unbalanced force is required, and the change in its speed or in the direction of the motion could continue as long as the unbalanced force applied. Unbalanced and balanced forces. Figure 9.3 shows a wooden block on a horizontal table. Two strings X and Y are tied to the opposite faces of the block as shown. If we apply a force by pulling the string X, the block begins to move to the right. Similarly, if we pull the string Y, the block moves to the left. But if the block is pulled from both sides with equal force, the block will not move. Such forces are called balanced forces and do not change the rest or the motion of an object. Now let us consider a situation in which two opposite forces of different magnitudes pull the block. In this case, the block would begin to move in the direction of the greater force. Thus, two forces are not balanced and the unbalanced force acts in the direction the block moves. This suggests that an unbalanced force acting on the object brings it in motion. Figure 9.3 shows two forces acting on the block and what happens when the children try to push the box on the rough floor. Now we move on to the first law of motion. By observing the motion of the objects on an inclined plane, Galileo deduced that objects move with a constant speed when no force acts on them. We observed that when a marble rolls down an inclined plane, its velocity increases. In the next chapter, you will learn that the marble falls under an unbalanced force of gravity as it rolls down and attains a definite velocity. By the time it reaches the bottom, its velocity decreases when it climbs as shown in the figure 9.5. Figure 9.5c shows a marble resting on an idle frictionless inclined plane on the both sides. Galileo argued that when the marble is released from the left, it would roll down the slope and go up on the opposite side to the same height from which it is released. If the inclinations of the planes on both sides are equal, and then the marble will climb the same distance that it has covered while rolling down. If the angle of inclination of the right plane is gradually decreased, the marble will travel further distances. It reaches to the original height. If the right side plane were to be ultimately made horizontal, that is, the slope is reduced to zero, the marble would continue to travel forever trying to reach same height that it has been released. The unbalanced forces on the marble in this case are zero. It thus suggests that an unbalanced external force is required to change the motion of the marble, but no net force is needed to sustain the uniform motion of the marble. In practical situations, it is difficult to achieve a zero unbalanced force. This is because of the presence of the frictional force acting opposite to the direction of the motion, and thus in the practice of marble stops after traveling some distance. Also, a small example is shown below how the body moves forward when there is an opposite brake applied. Uh, the effect of frictional force may be minimized by using a smooth marble and a smooth plane, providing a lubricant on top of the planes. Figure 9.5, the downward motion, B, the upward motion of the marble on an inclined plane, and C, on the double inclined plane. Newton further studied Galileo's ideas on the force and motion and presented three fundamental laws that govern the motion of objects. These three laws are known as Newton's law of motion. The first law of motion is stated as an object remains in the state of uniform motion in a straight line unless compelled to change, that state is applied by a force. The first law states about the inertia, the resistance of an object to a change in its state of motion or rest. Newton's first law says objects will continue in their state of motion or rest unless acted upon by an unbalanced force. Children, this is first law and you need to remember this quite well for the further studies in physics, which is very important to remember this. In other words, all objects resist a change in their state of motion in a quantitative way. The tendency of undisturbed objects to stay at rest or to keep moving with the same velocity is called inertia. This is why the first law of motion is also known as the law of inertia. Certain experiences that we come across while traveling in a motor car can be explained on the basis of the law of inertia. We tend to remain at rest with respect to the seat unless the driver applies a brake to stop the motor car. With the application of brake, the car slows down, but our body tends to continue in the same state of motion because of its inertia. A sudden application of brake may thus cause injury. Impact or collision with the panels in the front. Safety belts are worn to prevent such accidents. Safety belts exert a force on our body to make the forward motion slower. An opposite experience is encountered when we are standing in a bus and the bus begins to move suddenly. Now we tend to fall backwards. This is because of the sudden start of the bus brings motion to the bus as well as to our feet in contact with the floor of the bus, but the rest of the body opposes this motion because of its inertia. When a motor car makes a sharp turn at a high speed, we tend to get thrown to one side. This can again be explained on the basis of law of inertia. We tend to continue in our straight line motion when an unbalanced force is applied by the engine to the change of the direction of the motion of the motor car. We slip to one side of the seat due to inertia of the body. This fact that the body will remain at rest unless acted upon by unbalanced force can be illustrated through the following. Next, we talk about inertia and mass. All examples and activities given so far illustrate that there is a resistance offered by the object to the change of motion. If it is at rest, it tends to begin at rest. If it is moving, it tends to keep moving. This property of an object is called inertia. Do all bodies have the same inertia? We know that it is easier to push an empty box than full of books. Similarly, if we kick a football, it flies. But if we kick a stone of the same size with the same force, it hardly moves. We may, in fact, get injury on the foot while doing so. Similarly, in the activity 9.2, instead of the force and laws of motion, its velocity changes. That it is the object gets an acceleration. We would like to study how the acceleration of an object depends on the force applied to it and how we measure a force. Let us recount some observations from day-to-day life. During the game of table tennis, if the ball hits the player and it does not hurt him. On the other hand, when a fast-moving cricket ball hits the spectator, it may hurt him. The truck at rest does not require any attention when parked along a roadside, but a moving truck, even at speed as low as 5 meters per second, may kill a person standing in its path. A small mass, such as a bullet, may kill a person when fired from a gun. These observations suggest that the impact produced by the objects depend on their mass and velocity. Similarly, if an object is accelerated, we know that the greater force is required to give greater velocity. In other words, there appears to exist some quantity of importance that combines the object's mass and its velocity. One such property called momentum was introduced by Newton. Momentum p of an object is defined as a product of the mass, that is m, and velocity v, that is p is equals to mv. The momentum has both directions and magnitude. Its direction is same as that of velocity v. The SI unit of momentum is kilogram meter per second. Since the application of an unbalanced force brings a change in velocity of the object, it is therefore clear that a force also produces a change of momentum. Let us consider a situation in which a car with a dead battery is to be pushed along the straight road to give it speed 1 meter per second, which is sufficient to start an engine. If one or two persons suddenly push the unbalanced force to it, it hardly starts, but a continuous push over some time gives gradual acceleration to the car to get its speed. It means the change of momentum of the car is not only determined by the magnitude of the force but also by the time during which the force is exerted. It may then also be concluded that the force necessary to change the momentum of the object depends on the time rate of which the momentum is changed. The second law of motion, that the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of the force. So Newton's second law finally is made in short thing. An unbalanced force causes an object to accelerate. The acceleration of the object is equal and is net force acting on it divided by the object's mass. Mathematical formulation of the second law of motion. Suppose an object of mass is moving along a straight line with an initial velocity u. It is uniformly accelerated to velocity v in time t by the application of a constant force F through the time t. The initial and final momentum of the object will be p is equals to mu or p2 is equals to mv respectively. The change of momentum is proportional to P2 minus P1, proportional to mv minus mvu, proportional to mv minus u. The rate of change of momentum is proportional, or the applied force F is proportional to force which is equal to kma. This here it is the acceleration which is the rate of change of velocity. the quantity k is a constant of proportionality. The SI units of mass and acceleration are kg and meter per second squared respectively. The unit of force is so chosen that the value of the constant k becomes 1. For this, 1 unit of force is defined as the amount that produces an acceleration of 1 meter squared in an object of 1 kg mass. That is, unit of force 1 kg 1 meter per second squared, thus value of the k becomes 1. From the equation F is equals to ma, the unit of force is kg meter squared or Newton, is which has a symbol N. The second law of m into v minus u bracket t, m also is into bracket v minus u whole bracket t, then km into bracket v minus u whole bracket t. So motion gives us a method to measure the force acting on an object as a product of its mass and acceleration. The second law of motion is often seen in action in our everyday life. Have we noticed that while catching a fast moving ball, a fielder in the ground gradually pulls his hand backwards with the moving ball. In doing so, the fielder increases the time during which the high velocity of the ball decreases to zero. Thus, the acceleration of the ball is decreased and therefore the impact of the catching the fast ball is also reduced. If the ball stops suddenly, then its high velocity decreases to zero in a very short interval of time, and thus the rate of change of momentum of the ball will be very large. Therefore, a large force have to be applied for holding the catch. That may be hurting the arm or the palm of the fielder. In an high jump athlete, the athletes are made to fall either on a cushioned bed or on a sand bed. This is to increase the time of athlete's fall to stop after making the jump. This decreases the rate of change of momentum and hence the force. Try to ponder how a karate player breaks a slab of ice with a single blow. The first law of motion can be mathematically stated from mathematical expression for the second law of motion. F is equals to ma, that is when f is 0, v is equals to u for whatever time t is the time taken. This means that object will continue moving with uniform velocity u through the time. If u is 0, then v will also be 0, that is the object will remain at rest. Example 9.1, the constant force acts on an object of mass 5 kg for a duration of 2 seconds. It increases the object's velocity from 3 meter per second to 7 meter per second. Find the magnitude of the applied force. Now, if the force was applied for a duration of 5 seconds, what would be the final velocity of the object? Solution here is we have been given u is equals to 3 meter per second, v is 7 meters per second, and time is 2 seconds, and the mass is 5 kgs. From the equation mv is equals to ut, substitute the values for the following. F is equals to 5 kg, then 7 meters per second minus 3 meters per second divided by 2 seconds is equals to 10 Newton. Now, if this force is applied for a duration of 5 seconds, t is 5 seconds, then the final velocity can be calculated by rewriting the equation as u v t f t m. On substituting the values of u, t, m and t, we will finally get the velocity. The figure 9.8, a fielder pulls his hand gradually with v 13 meter per second, moving ball while holding a catch. Next is an example of a motor car moving with a velocity of 108 km and it takes about 4 seconds to stop after the brakes are applied. Calculate the force exerted by the brakes on the motor car if its mass along with the passengers is 1000 kgs. The initial velocity of the motor car u 108 kilometers per hour. Then next comes 1000 meter per second, and you can also see it is the final velocity of the motor car is v is equals to 0 m per second. The total mass of the motor car with its passengers 1000 kg and the time taken to stop the car is 4 seconds. From this equation we have the magnitude of the force applied by the brakes. M is equals to whole bracket V minus U over T. On substituting the values, we can get the result, that is 7500 kg per meter squared, or it can be also called as 7500 Newton. The negative sign tells us that the force exerted by the brakes is in the opposite direction of the motor car. Now, children, we will be moving to the third law of motion. The first two laws of motion tell us how an applied force changes the motion and provide us with a method of determining the force. The third law of motion states that when one object exerts a force on the other object, the second object instantaneously exerts a force back on the first. These two forces are always equal in magnitude but opposite in direction. These forces act on different objects and never on the same object. In the game of football, sometimes we see while looking at the football and trying to kick it with a bigger force, collide with a player of the opposite team. But both feel hurt because each applies a force to another. In other words, there is a pair of forces and not just one force. The two opposing forces are also called as action and reaction forces. Newton's third law. For every action, there is an equal and opposite reaction. In other words, if you push a brick wall, the wall pushes back with an equal force. And in simple words, it is called as for every action, there is equal and opposite reaction. A rocket is a good example to remember. When there is a force applied in one direction, the body of the rocket moves in the opposite direction. Okay, let's consider the two spring balances connected together as shown in the figure. The fixed end of the balance B is attached with a rigid support like a wall. When a force is applied through the free ends of the spring balance A, it is observed that both the spring balances show the same readings on their scales. It means the force exerted by a spring balance A on the spring balance B is equal but opposite in direction. The force which balance A exert on balance B is called the action, and the force of balance B on balance A is called the reaction. This gives an alternative statement of the third law of motion. For every action, there is equal and opposite reaction. However, must be remembered that the action and reaction always act on two different objects. The action and reaction are equal and opposite. Suppose you are standing at rest and intend to start working on the road, you must accelerate, and this requires a force in the accordance or the second law of motion, which is this force. This is the muscular effort you exert on the road. Is it in the direction we intend to move? No. You push the road below backwards, and the road exerts equal and opposite reaction force on your feet to make you move forward. It is important to note that even through the action and reaction forces are always equal in magnitude, these forces may not produce accelerations of equal magnitudes. This is because each force acts on a different object that may have a different mass. When a gun is fired, it exerts a force on the bullet, and the bullet exerts an equal and opposite force on the gun. This results in the recoil of the gun. Since the gun has a much larger mass than the bullet, the acceleration of the gun is less than the acceleration of the bullet. The third law of motion can also be illustrated when a sailor jumps out of a rowing boat onto the platform. As the sailor jumps forward, the force of the boat moves it backwards. Now, we are finished with the three laws of motion. Now, let's get on to conservation of momentum. Suppose two objects, ball A and B, say the masses of MA and MB are traveling in the same direction along with a straight different velocities UA and UB respectively, and there are no external unbalanced forces acting on them. Let UA bigger than UB and the two balls collide with each other. During the collision, which lasts for a time t, the ball A exerts a force FAB on the ball B, and the ball B exerts a force FBA on the ball A. Suppose VA and VB are the velocities of the two balls A and B after the collision respectively. Activity. You can also try some small activities at your end. Request two children to stand up in separate carts as shown. Give them a bag full of sand or some other heavy objects. Make them to play and catch the bag. Does each of them receive an instantaneous reaction as a result of throwing the sandbag? You can paint a white line on the cart wheels to observe the motion of the two carts when the children throw bag backwards. This is another example. Two hockey players of the opposite teams are trying to hit a hockey ball on the ground, collide and immediately become entangled. One has a mass of 60 kgs and was moving with a velocity of 5 meter per second, while the other has a mass of 55 kg and was moving faster with 6 meter per second towards the first player, in which the direction and with what velocity will they move after when they become entangled. Assume that the frictional force acting between the feet of the two players and the ground is negligible. The solution is the velocity of the two entangled players after the collision, the total momentum then m1 plus m2 60 plus 55 kgs and total comes to 115 kg per second, equating the momenta of the system before and after the collision in accordance with the law of conservation of momentum. We get V is equals to minus 30 over 115 is equals to 0.26 meters per second. Thus, the two entangled players could move with a velocity of 0.26 meter per second from right to left, and that is in the direction of the second player was moving before the collision. You can also refer this figure 9.1.9, the collision of two hockey players before the collision and after the collision. Let the first player be moving from left to right. By convention, left to right is taken as positive and thus the right to left is taken as negative if symbols M and U represent the mass and initial velocity of the two players. 1 and 2 in these physical quantities refer to two players, that is 50 kg plus 5 kg, and m squared is equals to 55 kg. Finally, the total moment of the two players is 30 kilograms as shown in the figure. Now that we have learnt the three laws of motion, force, inertia, and the conservation of momentum, let's move on to summarize what we have learned the last few minutes. Summary. The first law of motion. The object continues to be in the state of rest or of uniform motion along a straight line unless acted upon by an unbalanced force. The natural tendency of the object is to resist a change in their state of rest or of uniform motion called inertia. The mass of the object is a measure of its inertia. Its SI unit is in kilograms. The force of friction is always opposes the motion of its objects. So here the first law, please remember, inertia is the key word. Please remember about inertia when you want to recall the first law of motion. The second law of motion, the rate of change of momentum of an object is proportional to the applied unbalanced force in the direction of the force. Here, the SI unit of the force is kg per meter squared. This is also known as Newton and represented by a symbol N. A force of 1 Newton produced an acceleration of 1 meter squared per second squared on an object of mass 1 kg. The momentum of the object is the product of its mass and velocity and has the same direction as that of the velocity. Its unit is kg per meter second per second. Here it's simple to remember. The second law states about the acceleration, that is F is equals to ma. Please remember F is equals to ma to remember back the whole law. Coming to the point, third law of motion, it is to every action there is an equal and opposite reaction and they act on two different bodies. In an isolated system where there is no external force, the total momentum remains conserved. Here what we are talking about is, please remember a gun. For every action there is an equal and opposite reaction. So it's quite simple to remember the third law of motion. And about coming to the conservation of laws, all conservation laws such as conservation of momentum, energy and angular momentum, charge, etc., are considered to be fundamental laws in physics. These are based on observations and experiments. It is important to remember that a conservation law cannot be proved and it can be only verified or disapproved by experiments. An experiment whose result is in conformity with the law verifies or substantiates the law. It does not prove the law. On the other hand, a single experiment whose result goes against the law is enough to disapprove it. The law of conservation of momentum has been deduced from large number of observations and experiments. This law was formulated nearly 3 centuries ago. Interesting to note that not a single situation has been realized so far which contradicts the law. Several experiments of everyday life can be explained on the basis of law of conservation of momentum. Okay, children, we have gone through today's learnings. Now comes up the exercises which is available on the textbook. Please go through it and try to solve as many as possible of the exercises, applying the same different formula and the laws of motion. So this comes to the end of this chapter 9. So please complete the exercises at home. See you all in the next chapter. This is Surender signing off for Rural Public School. Thank you and have a good day.